In this video, we're going to go over notes 8 and 9 of the Unit 9 Thermodynamics notes. These will actually be the last two notes of AP Chemistry. Okay, so let's buckle in and let's get these done. Okay, so we're going to talk about phase changes. A couple things that are important that sometimes get overlooked is that delta G equals 0 during a phase change. And the reason why is that a phase change is considered an equilibrium process. Okay, that is because the gas or it depends on your state of matter. But let's say we're melting, for example. So we're going from solid to liquid. Some of those solid molecules will turn to liquid, and then they'll re-solidify, and they go through this a lot of times before they eventually become a liquid. And so they're going back and forth, and so that's a liquid, or that's an equilibrium process. Additionally, if we have a liquid, and that doesn't look like a liquid, and we're evaporating or boiling, those particles go up, they become gases, but they're randomly moving, so some of them will come back down and rejoin the liquid phase before they eventually get into the gas phase and stay there. So that's why it's considered an equilibrium process, but delta G is 0 during a phase change. I don't see this showing up a whole bunch during the AP test, but you just need to know the simple names of, solid to liquid, that it's melting. Most people know that. Liquid to gas, that's boiling or evaporation. The difference is if I have a liquid and the heat is coming from the bottom, that would be boiling. So the gas bubbles form at the bottom and then leave. Where evaporation, that would be heat coming from like the sun, so from the surface, the particles leave your liquid from the surface. And then these leave from the bottom. Okay, solid to gas, that's called sublimation. You have probably seen that if, like on Halloween or some other time you've seen a fog machine that typically uses solid carbon dioxide, which is called dry ice. And then going from gas to solid, that's called deposition. Going from gas to liquid, that's called condensation. And then liquid to solid, that's called freezing. So you just want to make sure that you know those. A heating curve, you've probably seen these before. We have solid, liquid, and gas. And then at 2 and 4, we have a phase change. And notice delta T equals 0 during a phase change. So a very weird phenomena that you might really struggle to accept would be if you have let's say on your stove you have dials for 1, 2, 3, 4 all the way up to 10, and let's say you're on number 4 and you have boiling water already in a pot. If you turn that pot or the stove up to 10, the liquid water in there is actually not going to get any warmer. Okay, because if it's boiling, the temperature of that solution or that liquid is not going to change. So at step number 1, if we want to solve for the amount of heat, we would do Q equals MC delta T. If we wanted to solve for the heat in part 2, it's still absorbing heat, it's just not changing temperature, we would use the heat of fusion, which would be a delta H value, just joules divided by moles, and if we wanted the joules, we would just need to multiply by the moles given. Okay, at step 3, we have temperatures changing. I know that because we have a positive slope, and so we would use Q equals MC delta T. At step 4, we're going from liquid to gas. That's a vaporization, so we would use the heat of vaporization. That's typically going to be abbreviated delta H VAP, where heat of fusion is just a fancy word for melting, would be delta H FUS. And then at part 5 of this, the temperature is changing, so we would use Q equals mc delta T. Now, the only difference here between these Q equals mc delta T's is that number 1, we have a solid, so we would need to use C for the solid. At number 3, we have the liquid, so we need to use C of the liquid, or the specific heat of the liquid. And then at 5, we have a gas, so we need to use the specific heat of the gas. Okay, so what is exactly happening here? At A, we have solid. Or A to B, we have solid. So essentially, your solid is warming. But notice we have a double-headed arrow, so we could really say, or the solid is cooling. And here we would have the solid is cooling. It has a negative Q. It's releasing heat to the surroundings. And if the solid is warming, we'd have a positive Q. From B to C, we have no change in temperature. And our solid is then phase changing. So solid is melting. But it's also in equilibrium. We have double-headed arrows, so we could also say, or our liquid is freezing. From C to D, we have a change in temperature. So we could say that the liquid is warming. But we have double-headed arrows, so we could also say the liquid is cooling. Again, if we're cooling, that would be a minus Q, and if we're warming, that'd be a positive Q. From D to E, it's flat, the slope is 0, so that means phase change. We would need a delta H to get Q over moles if we wanted to specifically solve for the Q. So that we could have liquid boiling, or we could have liquid condensing, or excuse me, gas condensing. And then in part E, we could say our gas is warming. Be a positive Q, or our gas is cooling. That'd be a negative Q, just depending on which way that we go. Okay, so factors that influence phase change, it's going to depend on your atmospheric pressure. We're going to talk about that in just a second. The strength of the forces holding your particles together. So, for example, we have LDFs, we have dipole-dipole, and then we have H bonding. And you might remember a phrase that we said. We said high IMFs equals high, whatever the property might be, high boiling point, freezing point, melting point, all of that stuff, except, and maybe you remember the one exception is vapor pressure. So that's kind of a nice thing to remember. It's not a justification, it's just a way to kind of memorize. Obviously, the temperature is going to make a difference. It's going to influence whether or not a phase change can happen. You've got to reach a certain threshold of pressure and temperature, and then it depends on the identity, and that goes back to your intermolecular forces. Okay, so LDFs, these have really low boiling points, where things with hydrogen bonding have really high boiling points, freezing points, melting points, all that. Okay, so vapor pressure, if you remember back to the gases unit, and I'm gonna draw this here. Think about, we have a beaker of water, and I'm just gonna use a circle to represent our water molecules. we will have some of those particles in the gas phase, okay? Think about just like a hot tub with some humidity. The higher the temperature, the higher the vapor pressure, because more particles will be able to enter the gas phase. Okay, so if we lower the pressure, pressure is what pushes down on here, and I always kind of think about the pressure pushing down and pushing these particles down into the liquid phase. If we let up on this pressure, so let's say instead of having a big arrow here, we have less pressure. If we lower the pressure, the boiling point lowers. And this is because with less pressure, it becomes easier to enter the gas phase. Now, what happens if I increase the pressure? Some of these gas particles are going to go away and they're going to go back into the liquid phase, okay, with a higher pressure. And so that's going to cause your boiling point to raise or increase. If you've ever traveled to Colorado, specifically like Denver's called the Mile High City, and that's because the higher you go, the less pressure there is, and so it becomes harder to cook food. Like if you want to boil chicken, for example, water boils at like 96 degrees Celsius in Denver, so you have to cook your food longer to make sure you're killing any of the bacteria because the water doesn't get as hot as it does, let's say, in Indiana, where the sea level is much lower. Okay, so what we're going to see is a nice trend here that if we lower the pressure, the melting point is going to lower, the freezing point is going to lower. If we raise the pressure, the melting point is going to increase, and the freezing point is going to increase. Okay, and it's essentially because the higher the pressure, the more force causing your particles to come closer together, and they're more likely to be in the solid phase. But if we lower the pressure, the more we lower it, the less likely it is to have a force bringing those particles close together. Okay, and so we see this all summarized. This is a really nice graph summarizing everything that I've just talked about. Okay, last set of notes, and this is a nice set of notes because in this unit we've seen a lot of formulas and everything's sort of come full circle where we've seen formulas that we were first introduced to, let's say, in electrochem, and now they've kind of come back. So let's talk about what sort of information you need to be given in order to use these specific formulas. So delta G equals minus RT ln of K. If we're going to solve for delta G, here's what I know. R is 8.314 joules per mole Kelvin. R is only, 0.0821 atmospheres times liters divided by moles times Kelvin in PV equals nRT. Or when using molar mass equals dirt over P. That's the only time R is going to be 0.0821. Your brain likes to use this because that was the first time you were introduced to an R all the way back in regular chemistry. So that's what R would be. T, that just depends, but if we're at naught, then T is going to be 298 Kelvin. But what must we be given? We must be given equilibrium information, like a Rice table or just given K. Okay, what if we're solving for delta G and it's equal to minus NFE? N, if you remember, is the number of moles of electrons that cancel. So for example, if I have aluminum plus 3 electrons goes to aluminum, let's say I have nickel goes to nickel plus 2 electrons. 3 and 2, the least common multiple would be 6 there. we would need to be given electrochemistry info like volts. And we would do E cell equals E cathode minus E anode. Okay, this one's a Gibbs-Helmholtz equation. Here we would need to be given delta H or delta S, and then temperature if we're not under standard temperature. This formula, I have a small typo here. I need to add the capital sigmas. Those are summations, which means we're going to take the sum of all of our products and the sum of all of our G for our reactants. And you would be given a table of G values. That would be, it looks something like compound, just let's say X and Y, and just say a G value 23, 25, and that would be joules per mole. By the way, I want you to write down here somewhere, delta G is always joules per mole. Okay, mathematically that's what it always is. And then Hess's law, that might look, and I might not have this right where it would actually add up here. I'm just making up stuff for argument's sake. We might have and it would be like delta G for this reaction is 5, delta G for this reaction is 24, and we might need to like multiply this one by 2 and then flip this one, do stuff like that. But because this is delta, we would just take, if this is reaction A and this is reaction B, we would just take, we change these delta G's however necessary. They might be fine the way they are, or we might need to change them, but we would just add the delta G's. Okay, enthalpy. So when would I use a formula like delta H equals Q over mole? Your problem might give you Q equals MC delta T type problem. And then to get delta H, we would just get moles of your reaction, or moles, if it's not a reaction, just your moles of substance. Okay, if we're solving for delta H here, we would need to be given delta G and delta S. But remember, I could see them doing a way where they give you K. If they give you K, you can get delta G equals minus RT ln of K. So they don't have to directly give you delta G for you to need to use this equation to get delta H. Now, delta H, typically, it's given in kilojoules per mole, and you need to convert to joules per mole. Okay, the only way the math works out is if it's in units of joules. Okay. If we're given delta H equals the sum of H products minus the sum of H reactants, we're going to go back and I'm just going to copy this and I'm going to paste it because we would solve it exactly the same way. I call these deltas. So instead of it being G values, they'd give us a table of H values. Going back to the bonding unit, and this formula is not on your formula sheet, we could have bonds broken minus bonds formed. What would you be given to use this is you would be given a table of bond energies. Okay, so maybe it would say something like bond, we have X, Y, and that H value, the heat needed to break that bond would be, let's just say 23 joules per mole. although it'd probably be kilojoules in a table. Let's say we had HCl, and let's say that's 46. Now, make sure if you have something like 2H2O plus oxygen, it just goes somewhere, we would need to make sure that we have a good Lewis structure, and we see that 2H2O would really be breaking 4 OH bonds, okay? So those coefficients are important there. And then Hess's law, same exact thing here, I'm just going to copy and paste it. We would solve it exactly the same way, except instead of given delta G values, we'd be given delta H values. Okay, last page of all of AP Chemistry notes. If we're solving for entropy, entropy is in units of joules per mole. A lot of people get that part right, but they commonly forget the Kelvin that's in the denominator. Okay, so if we're solving for delta S, we would need to be given delta H and delta G, and we don't necessarily have to be given delta H just like that or delta G just like this. On the previous 2 pages, we've seen there's lots of ways to get delta H and delta G. If we're doing the sum of S products minus the sum of S reactants, going to be solved exactly the same way. We'd have to be given a table, but for entropy, it would be of S values. And joules per mole Kelvin would need to be the units. And then if we were given Hess's law, again, delta S is solved for similarly to delta H. The only difference is we would have an S here. And so these notes are just to help you kind of think through all the things that we've done all year long that you want to be able to be pretty fluent in, so you don't have to spend so much time on your test or your AP test really trying to think about these. These kind of want to become very natural for you to go in between.